Avoiding common finite state machine errors. Cover every possible branch with every if case to avoid latches. We learned about that. So here we have always at state, say these are the inputs A, B, or C begin. Make sure that, well, here's one way to do it. If I make the next state S1 at the beginning and then I update the values later on, I'm guaranteed there's no latches. No, we don't, this is meant to be just combinational logic, right? We don't want any latches. And if we want to avoid latches, in this case, next state has to be updated in every possible branch, okay? So one way to do that is next state at the beginning and then update it, or make sure every block, every if then else, it's updated. State must be in the trigger variable if the procedures update the next state. So that's another common error that people make. This state has to be right here. If you don't put that state, you get snaz, right? Because this state comes in here. It's an input. If we don't add state as an input to this logic and the state changes, then we may not change the outputs the next state until X changes. And we don't want that. That's not how it really works. So state must be a trigger variable. The state must be in here as well as the other inputs. A variable on the left-hand side of the equal sign must not be a trigger list. We learned that before. So if A is on the left-hand side, we don't want A in the trigger list. That's an endless loop. End all case statements with a default case. We already talked about that. I put this in red. Every time you see something I highlight in red, that's super important, right? So make sure you do that. Do not forget the self loops in your state. So here's a self loop. If you have reset, you're coming back, then you can have if reset, A or B and C go this way, else if C and D go this way. But very commonly people forget this state, else the next state equals reset. So, or whatever the name of the state is, but don't forget those self loops. It's a common error. Always partition the finite state machine into these 4 blocks we talked about. And always use this less than an equal for the register procedure, not an equals. So this always at pause edge clock. It's a less than an equals, not an equals. For simpler finite state machines like counters or shift registers, you don't need to divide it all into this 4 blocks. So for instance, here's a counter that in some Verilog code. This counter has a bunch of flip-flops that have count values. And then we also have this terminal count. When all the values are equal to 1, all these ands add up and terminal count equals 1. So that's kind of like a little finite state machine, but instead of breaking it up into a section, we can put it all into one little procedure. It says always at clock, pause edge clock, or pause edge reset begin. If reset, the count equals 0, else the count equals count plus 1. And then we have this assign statement for this logic that says the terminal count equals anding of all the bits of count. So this little state machine was all done in one procedure. The next state, you can think of count as the next state. It's all built in with the logic as well. And you'll notice we've used a reset here. And the reset can be pause edge or neg edge as well. And we'll talk more about this. When we put the reset in the trigger list, we call that an asynchronous reset because it'll happen even, it's not shown here, but these flip-flops have a reset coming into them, and we don't need to wait for clock. If reset goes high here, then it'll all reset. And then we make the condition, assuming the reset is going high. When the reset goes high, we test for the condition that reset is high, and we set the count equal to 0. If this was a neg edge reset, we wanted to reset on the neg edge like that, then this would have been reset bar instead of reset. When test for reset is low, count equals 0. So this can be a pause edge reset or a neg edge reset.
Professor.
Yep.
So if we want to specify a negative edge reset, can we also physically write that into the trigger list? Can we say neg edge reset, or do we just always use the bar?
We do both. If we want, this would have to be neg here. This would be neg reset. N. E. I don't know if you can see this very well. G. I have to go really slow with this tool. This is, instead of pause, it would be neg edge reset, and I'd put the bar here.
Okay, thank you.
Yeah. So you can have pause edge or neg edge clock, and you can have pause edge or neg edge reset. Here's an interesting question. Oh, did we already talk about this? Remember I told you, somebody asked me one day, oh, how come they always use negative reset? This is more common to use neg edge reset, right? Remember we did that thing when two chips tie together and we want to have a wired OR function? We like a negative reset. So yeah, you will see the neg edge more commonly. Inside the chip, it's not so important. It's just when you're connecting to the outside world that it's very common to use neg edge reset. Any questions? Yeah, any posits you use the non-blocking assignment. So yeah, we use the non-blocking assignment here. Here's another simple finite state machine, which is a shift register. The operation less than n shifts left n bits, greater than n shifts right n bits. So this says 3-bit register Q, always at pause edge clock or pause edge reset. If reset, Q equals 0, else begin. Q equals Q left shifted 1, so it takes all the bits and shifts them 1. And then Q0, that's this one, is going to be equal to the Q3 value. So here's an important case where this is really important to use this non-blocking, because you see what happened here with this procedure. When I grabbed the procedure, the flip-flops grab the values of these Qs, right? Q0, 1, 2, and they decide the new values based on those values. If I didn't have this non-blocking thing here, if I just used a regular equal sign, what would happen is it would say, oh, first do, so let's say I forgot that, and I forgot that. It would say, okay, do the shifts. So it would shift all the bits around. And so now the input to this first flip-flop would be Q2, right? Because the Q2 would have come out here and would have been done here. And then when I do the second one, Q0 would have been equal to Q2, not Q3, the old Q2 value. So the non-blocking prevents that from happening. It just says use the values of Qs when you started the procedure. And that's the way the real circuit works. So the old Q3 is sent to Q0, not the new one, not the revised Q3 from the previous line. Can you see that? That's an important concept. Yeah. So the non-blocking operator, less than equal, for variables on the right side of the less than or equals, Q here, are grabbed as the procedure is triggered. The old values are used for calculating the left-hand side. And that's important. And in fact, we use this for both flip-flops, or if we just want to build latches by themselves, it's preferred to use this as well. Latches, it's a little bit questionable, but it turns out overall, if you're not logic, but if you're just building latches by yourself, and we'll see some examples later how to build latches, we use this as well. Now, as I mentioned earlier, we tend not to want to use latches. Most of the time, we're just using flip-flops and logic. Latches are a special case. Any questions about that? I'll bring my chat back up here in case anybody has chat.